Alright, the first unit, or technically the 6th unit, and the first lesson of the 6th unit. The first one on my channel though, so Angular Kinematics. That would be our first. And yeah, just to start off, I think it may be best for us to consider what we know about linear kinematics first. Just a quick review, which it's basically just a sort of system, per lack of a better word, that we use to calculate motion. For example, it deals with acceleration, right, velocity, and distance, or meters, I guess, if you want to call it that. And it just deals with distance in a linear fashion, whether you're moving at a constant velocity or you're moving with a constant velocity and the object is also moving with a constant acceleration, or whether you're just trying to calculate a certain distance that the object has moved, right? And that's our distance d here. And that's what angular kinematics is. But this means that when we consider angular kinematics, right, we have a bit of a lopsided circle here. In fact, I think I have a circle tool, don't I? Oh, I do not. Okay, that's my bad. Regardless, we have circles, right? But when you envision a circle and you envision a point on that circle, and that point is moving around the circle, it's not really a linear movement. You can't really use these lines to calculate the motion or how long, sorry, I can't speak, or to calculate the distance which this object is moving, at least not any meaningful degree. Because this point, if it were directed just slightly here with a different radius, slightly below it, would now be moving a completely different amount of direction. So it's very hard to create a sort of universal set of equations for it. Which is why for kinematics, you cannot be calculating meters or distance in the same fashion. The only thing you can do is calculate the only thing which will remain constant for this circle and this circle. And that thing is angle. Now, aside from that, I don't think angular kinematics is too different from normal kinematics. The same principles still apply. You still have distance, except now instead of meters, it's theta, degrees, or radians if you prefer, which I would prefer, so let's go with degrees. So distance is now just, did my brush lower? Sorry, it definitely did. I was using this. That's really awkward. I digress. Sorry, back to where we were. I was saying that it's the same thing as normal kinematics, but distance can no longer be measured in meters, but rather in radians now. So whatever distance you have, it'd just be in radians, or in an angle of some sort. Now this means that velocity now it just becomes also in radians. And just like distance was distance over seconds, now that we're using radians in place of distance, we can just sort of substitute radians for distance, and you end up with radians over seconds. Now, some of you who have already progressed, I think it's past pre-calculus where you first learn about radians, will know that radians don't actually have a unit. So what this really is 1 over second. And that's why you would see these written in both forms depending on where you are. Because they, but yeah, what you really need to keep in mind is that they mean the same thing. They're not different. Sorry, so yeah, to recap, distance equals radians, which means that velocity is radians over over seconds. And likewise, acceleration would be radians over seconds squared. Nothing new here. Nothing new here. You're just replacing distance with radians. That really needs to be grounded into someone's head, because it really helps to simplify this seemingly difficult subject into something that is much more maybe intuitive is not the right word, but something with which you have more experience. On the subject of radiance and of velocity and acceleration, since this isn't technically equal to velocity, right? Because velocity would be written as meters over seconds, and acceleration would be meters over seconds squared. We get to give these a new name, and what those names are is R is plural. I digress. Those names are essentially alpha for acceleration, which alpha, again, is just radians over seconds squared. Simple stuff. And an omega for velocity, which is just radians over seconds. Again, nothing really new. We're just naming these things so we can refer to them easily. And likewise, distance is just theta or degrees. Or sorry, not degrees. Again, we're doing radians. I'm just, it's in my mind, degrees. It's stuck in there. And yeah, that's really just the big general thing. Now, besides all that, we now get to, actually, I guess, yeah, for a quick recap. Radians should be explained. I feel it might be best. This is just a normal circle. This would be 0 degrees, 90, 180, 270, and 360, right? And you just have 45, 30, 60, normal stuff. Now, if you want this in radians, which again, radians is just a different measure of angle, thereby degree. All you need to know for radians is that pi radians is equal to 180 degrees. If you want to know why it's pi, which seems like an obscure number, I really suggest you Google that. It's a bit not too heavy of a topic, but it's a lot to talk about. And I don't want this to be too long. But it essentially boils down to circle, circumference, sorry, anything to do with a circle or, its circumference area, all that has to do with pi. Radians or degrees is kind of a measure of the circumference, which is why it includes pi. And that's just the general gist of it. So yeah, pi equals 180 radians. That means that at 0 degrees, it's still 0 degrees, obviously, because the conversion factor, if pi is equal to 180 radians, is just to divide both sides by 180, and you have 1 degree equals pi over 180 degrees. So if you want to convert 0 degrees, right, it's still just from degrees to radians, you just multiply this by what degree you want to get, pi times 0 degrees, it's still 0, which is why this is still 0. I should not have a degree symbol there. Where's my eraser? Oh, that's an odd looking eraser. Nonetheless, yeah, that's the truth of it. Well, since that's 0 degrees, and we know that pi is equal to 180 degrees, we can likewise put pi radians, I keep calling this degrees, radians at this end of the circle, which means that this has to be pi over 2 degrees, because it's halfway between these two. And this is going to be 3 pi over 2 radians, because it's 1 plus halfway, right? And likewise, we know that 260, which is just 2 times 80, would be equal to 2 pi, because 2 times pi would be 2 pi. And that's just, the basics of it. More or less all that you need to know. Yeah, so I'd keep, or at least write down that 1 pi radians equals to 180 degrees. That's really important. And also write these down from way back when. Yeah. So that's a good starting point. Now, angular kinematics. There is really 2 types of motion they'll hit you with over there on your question sheets. You have the circular motion, and you'll have rotational Wow, that is some horrid writing. That's my bad. Rotation. No, now that is not how you write rotational, but you know, this is not English class. Lucky for me. Circular is just one point on a circle, and it just continues. Rotational is just the entire circle rotating, which means that technically speaking, one rotational movement is equal to 2 pi radians of a circular movement, or you know, angle change, whatever you want to call that. I think movement is a bit intuitive, so it helps to call it as much. And yeah, on the subject of circular motion, I feel like a lot of times when we envision it, we see a point go around a circle, and it goes and goes and goes and it comes back. So we're very inclined to say that it didn't move at all. But that is obviously not true, you know, we know it moved 2 pi radians. So a much better way to kind of envision it is rather as a spiral. I don't think I can draw much of a spiral, and I apologize for that. Maybe it'll be easier. That's the wrong button. If I draw it this way. That's somewhat easier, but it's besides the point. It's easier to envision circular movement as a spiral, so you don't forget that each rotation also counts. It's not 0. And yeah, that's this beginning part. So from here, let's sum up all that we know so far. We know there is circular, 1 point, and rotational movement. We know that the distance is measured in radians. We know that we can calculate the angular velocity as radians over circle. I said it again, over seconds. And we know that we can calculate the angular acceleration as radians over second squared. So what do we actually do with this information? We don't really want to go ahead and invent a whole new system for angular kinematics when we already have a perfectly reasonable and useful, not to mention correct, system for linear kinematics. So it'll be much easier for us if we can find a way to convert between angular and linear kinematics or motions. And yeah, that's definitely much easier said than done, but it's also not. It seems a bit scary at first. But to do this, well, it's not too bad if you're a bit familiar with calculus concepts. When you're taught calculus and you try to find a derivative of, say, sine, alright? You're given a sine function of, that is not what I meant to do. In fact, let's just do this, of a certain angle theta. And you're told to find its derivative, which is an instantaneous rate of change. It's obviously not easy to envision. So usually how, when you start out, you envision instantaneous rate of change is just a slight nudge that's nearing 0 to whatever it is. So if, say, you have some area, and you want to give it a slight nudge that's near 0, you just, you know, draw the barest of a nudge to its area. And this area really just gets infinitely smaller because age is approaching 0. It keeps going lower and lower and lower, you know, 0.01 and then becomes 0.001 and so on and so forth. So a slight nudge to an angle would be this theta, and then you just draw this new theta, right? And this here nudge, which that's not very fun to look at, but this nudge is equal to some degree theta, or some radian theta, and we know that this same degree theta is approaching 0, getting infinitely smaller. This means that you could draw a tangent line to it, right? Because that's derivatives in a whole. And the slope of this line is equal to the theta at which this little guy here accelerates, which the radians in which the theta increases. Sorry, that's a much better way to phrase it. We could call this nudge delta x, and this line here we know is the radius, obviously. Now, that's cool and all, but what does this even tell us? Well, if you've calculated tangents of really small numbers and sines of really small numbers, you know that as theta approaches 0, it becomes equal, the tangent of theta will become more or less equal to the sine of theta, which in on itself will become more or less equal to theta itself. In radians, mind you. Well, I mean, it's also true for degrees, obviously. They, as we mentioned, pi equals 180, they convert pretty linearly. But yeah, in radians. Now, what does this tell us? Well, this tells us a lot, because we know that if you have the tangent of an angle theta here, and tangent, remind you, is equal to opposite over adjacent, you would know that we know that this is what tangent is equal, and this right here is what our triangle looks like, right? Creating all that stuff, all that goodies. So we know that the radius here is the adjacent, this angle theta, and this right here is our opposite to that angle theta, with this obviously being our hypotenuse. Now, what does this tell us? Well, this tells us that a tangent of this angle theta is equal to this delta x, which, I'll remind you, is just theta getting closer and closer to 0, over the radius of the circle, big R, radius. And using this, since we know, again, that tangent of theta is essentially equal to theta when these numbers get increasingly smaller, we know that this angle theta is equal to change in x divided by the radius. And this right here allows us to convert between angular and linear momentum. This is the golden equation, if you will. Essentially, we can plug this into the equations we've made before, the ones that said omega equals theta over second, and alpha equals theta over second squared. And likewise with them, we can, went to the side, sorry. Likewise with them, we can remember our normal kinematics equations. Velocity equals meters per second squared. Acceleration equals meters per second squared. This is not a square, this is just per second. And now we get to just mix and match, we get to plug in. So we have this, right? And likewise we have this. So theta and theta, well, we know, we could just plug that in. So this tells us that omega is also equal to a change in x divided by radius over seconds. I'm being called. Would you look at that? I'm back. Right, where were we? Oh yeah, we were just substituting theta in for this theta, right? Because we know that. And essentially, you'll get this equation here. Now, delta x over seconds. Velocity is equal to x over seconds, is it not? Well, it is. And this also tells us that omega is actually just equal to velocity over radius. Very simple, It's a very easy conversion factor, which is good. We like that. And you can do the same thing with alpha here. Alpha equals theta over second squared. Actually, I'd encourage anyone watching to do this on their own real quick, just to practice, because it's not too simple. I feel very intuitive, not too hard. I feel it's very intuitive, and it's a good bit of practice that'll really help nail it down in your head. All right. So yeah, substitute this in for theta. What do you get? We get alpha is equal to delta x over r, oh, I forgot my x, over second squared. And again, you have delta x over second squared. This is equal to acceleration over radius. Don't forget this. And yeah, that's also the conversion factor between alpha and acceleration. Alpha is equal to acceleration over radius. And those are mainly the big equations for this unit, I'd say. Well, you know, they help you obviously sort through the rest of the kinematics. For example, let's take one of the easier equations of kinematics. Velocity final is equal to velocity initial plus acceleration times time. Well, if this is equal to this, we know that acceleration is equal to this over radius. Or sorry, we know that we can just divide acceleration by radius to get this. That's easier to work with. And obviously same thing for omega. You can divide velocity by radius and you get omega. So let's divide by radius, right? Over radius, over radius, over radius. Simple stuff. Velocity over radius, that's omega. Velocity over radius, that's also omega. Acceleration over radius, that is alpha. Well then, this kinematics equation, if you want it in angular kinematics, is just omega final is equal to omega initial plus alpha times time squared. This is time. No, it's not time squared. What am I talking about? Oof, I got a few of my equations mixed up. I thought we were solving for distance, not velocity. But yeah, and this is a kinematics equation. I'd write this down in a separate piece of paper that's just easy to look at. It'll make your life a bit easier, I imagine, when you're solving whatever worksheet you need to. I write this down as well as the other three kinematics equations, which are delta x equals 1/2 times v final plus v initial by t. Delta x equals v initial by t plus 1/2 acceleration by t squared, and v final squared equals v initial squared plus 2 by acceleration by delta x, which, what did I do? Oh, that's what I did. Sorry. Which, if we convert into angular momentum by simply dividing everything by radius, as we've done before, simply tell us that delta theta equals, because theta, I'll remind you, from way back here is equal to delta x over r. Big R as in radius. Delta theta is equal to 1/2 times, that's an odd looking 1/2. We're all odd looking. Times omega final plus omega initial times time. Time stays the same because it's multiplied and the r goes to these functions. So you just have this times time. I feel like that might be maybe useful to mention. I don't know. This function can be rewritten as delta theta equals omega initial times time plus 1/2 times alpha times time squared. And lastly, this function, which is probably my least favorite, mostly because of these, but that's irrelevant. This function just tells us in angular momentum, I keep calling it momentum, angular kinematics, that omega final squared is equal to omega initial squared plus 2 times alpha times delta theta. because you multiply everything by radius again. You don't multiply time by radius if you can help it, but everything else should be multiplied by radius. This makes no sense. Because you just divided everything by radius, didn't you? Well, it's velocity squared. Velocity squared is equal to, what, meters squared over seconds squared. Oh, yeah, that's... So, yeah, sorry. For this one, you'd have to divide by radius squared. So, it simplifies everything. The squares can just be taken out for u. And you just get m over s over r. Same with this one. And then for this one, you can just write it as r times r over acceleration times delta x times 2. And then these just go together and these go together. Sorry, that's my fault. I was not prepared for that. But you know, that's why we learn. We teach. That's why the Feynman technique is so powerful. It really helps you catch your mistakes and where your understanding is lacking. Even when you're just teaching a non-responsive entity, as everyone watching currently is to me. It didn't come out very well, did it? Sorry, so yeah, these are our big equations. I'd write these down. They're important, they're useful. They're how you'll get work done. You got just 1, 2, 3, 4. And they're the good life. Yeah, aside from these, the only other formulas you need to know are... do they exist? I can't think of any off the top of my head. 1 over frequency. Frequency is equal to seconds, though. Oh, right, sorry. If you're trying to, or if you're given a problem that gives you information in the form of period and frequency for loops instead of, you know, being nice to you, then that's not too hard to work with, because frequency, or sorry, period, the, whatchamacallit, units for that. Hi. I'm just gonna correct what I was technically, I guess, about to say. Yeah, the other equations. Essentially, you know, this frequency is equal to 1 over seconds. Period is 1 over frequency, which is there by just seconds. Using this knowledge, we can just rewrite our formulas as angular velocity is equal to 2 pi times frequency, which can also be written as 2 pi over period, just in case you get information given to you in frequency and period. And yeah, obviously you could use this to plug it into acceleration if need be, or it's gonna be like, you know, frequency squared or whatever. Yeah, that's that. Bye. It actually works out really well that this is the one I forgot, because this doesn't really come up again in the rest of this lecture. So we'll just continue on. And yeah. Whew. Okay. So where did I leave off? Right. If you remember kinematics unit, you'll remember, I'm sure, with... Well, actually, it wasn't that bad. I actually enjoyed it a bit. I think the general consensus of my classmates was that graphing, because it gave you all kinds of graphs of v over t and that kind of stuff. I think most people dislike this. And I'm sure you would, this is actually a lowercase d, I'm sure you'd dislike it even more if you had to learn completely new ways to graph this and transpose between velocity and acceleration by time and meters or distance by time. And I'm happy to note that you don't really need to learn any new method. You can simply plug in omega, alpha, and theta for their respective counterparts, and you get stuff like theta by time, right? And that's just this graph. Well, the area under this graph is still equal to omega, which is the counterpart of velocity, by time. So there's nothing to worry about here. Likewise, you know, the slope of omega time by time graph is still equal to theta by time graph, because, you know, you're taking it at each individual moment, which is how you get a graph. Cool stuff. And the area under this is still equal to theta, which is the counterpart of distance by time graph. So, you know, simple stuff. Yeah, and obviously for this, gosh, my head is not working with me ever since that thing over here. But sorry, I digress. Slope of this is still equal to this stuff over here. And yeah, that's most of it. Oh, another thing. Getting caught up with revolutions seems not like the democracy, Hamilton, those kinds of revolutions from way back before, where, you know, it's just going in a full circle. Getting stuck with those also seemed to be something that I was seeing with my classmates. So I just advise to remember simply the number of revolutions is simply equal to radians over 2 pi. This is intuitive. A lot of people just thought that this was just a random equation that was given out of nowhere, but no, because think about it. So this is delta theta. You have a circle, and you're moving along the circle. The amount that you move is your delta theta, right? A full circle is simply 2 pi. Nothing to worry about. So if you want to find the amount of revolutions, you just need to divide how much you've moved by how many circles. You know, it's just basics of division, in the same manner that if you moved a certain amount x, and we decided to call a full, or a revolution, or a full circle, some amount over here, we'll say is a constant at 2. You simply need to divide x by 2 to see how many revolutions, or this amount, we've moved. And that's all there is to it. From here on out, it's simple stuff. Yeah, so let's do just a quick practice problem, I guess. Let me look for a good one from my homework sheet. Alright, I've got 3 good ones for my homework sheet. We've got number 6 here, number 8, and number 9. So number 6 tells us that a flywheel slows from 250 rounds per minute to 150 rounds per minute, or rounds as in revolutions, in just 4.2 seconds. And then it asks us to find how many revolutions happened during this time. So let's just write down what we know. We know that our initial angular velocity was 250. Rounds per minute is just, a round is 2 pi, a minute is 60 seconds. It tells us our final angular velocity was 150 rounds per minute. Tells us time was 4.2 seconds, and it wants to find number of revolutions. Number of revolutions is just theta over 2 pi, so it really wants us to find theta. So we need to find an equation that uses these 4, what do you call them, inputs? That's not the word, but yeah. And yeah, that equation is the hidden equation, the second equation, which states that delta theta is equal to 1/2 times final velocity angular plus initial angular velocity times time, which then if we plug in numbers, delta theta equals half times 250 plus 150, both of these are 2 pi by 60. So let's rewrite them. 250 plus 150, that's 400. That's a good button to press self. So yeah, let's just rewrite that as simply 400 2 pi per 60 times time, and our time is 4.2 seconds. And here we just plug all this into the calculator, and we get that delta theta is equal to, that is 28 pi. 28 pi, easy number. So to find the number of revolutions, we need to divide 28 pi by 2 pi. Pi cancels out, 28 divided by 2, we get 14 revolutions. And that's number 6. Oop, did it again. Oopsie daisy. Yeah, you know it's number 6. Yeah. Number 8, a ball rolls down a 1 meter long incline. So delta x equals 1 meter. From rest, so initial velocity equals 0 to 2 meters per second. So final velocity equals 2 meters per second. And the ball has a radius of 5 centimeters, so radius equals 0.05 meters. And it wants us to find the angular acceleration. Well, this right here is an angular, but all this is in linear kinematics. So we need to convert using the radius, which we were given. That means we divide everything here by 0.05, and we end up with theta is equal to 20 radians. Our initial angular velocity is 0 still. Our final angular velocity is 2 over 0.05, that's 40 radians per second. And yeah, now we just need to find an equation that has theta, initial and final angular velocity, and alpha. And that equation is our fourth equation, which states that final velocity, angular velocity squared, is equal to initial angular velocity squared plus 2 by alpha by delta theta. Let me draw parentheses here. And yeah, now we just get to plug. So you have 40 squared equals 0 squared plus 2 by alpha by theta. Theta is 20. So now we just need to isolate this variable. This doesn't matter. 2 times 20 is 40, so alpha is equal to 40 squared over 40, which is 40 radians per second squared. And that was number 8. Now number 9. And number 9 says a soccer ball is rolling at 15 radians per second, so initial angular velocity equals 15 radians per second. And it stops rolling, so final angular velocity equals 0. After traveling 25 meters, so delta x equals 25 meters. Yeah, delta x equals 25 meters. And it wants us to find the time. And wants us to find the angular acceleration. And it tells us that the diameter, not the radius, diameter is 20 centimeters, and that just means that the radius is 0.01 meters. So yeah, let's find one of these first so we can find the other. I prefer to find angular acceleration first. So let's look for, oh, I'm sorry. First, let's make sure that we have everything in angular terms, or at least on the same term. So let's divide delta x by 0.01, and our delta theta is a simple 250 radians. And now let's find an equation that uses initial angular velocity, final angular velocity, theta, and not centripetal, angular acceleration. I keep calling it centripetal in my head, and I don't know why. Well, I do. Besides the point. Yeah. Okay. That's the same equation as this one here, right? So we have final angular velocity squared, final angular velocity squared is equal to initial angular velocity squared plus 2 by angular acceleration by delta theta. And now if we plug in numbers, the numbers that we were given, we find that 0 squared minus, we're just moving this to this side, so it's a bit easier for us to work with, minus 15 squared is equal to 2 by theta by 250 radians. So 15 squared is, what is that, 225? Let me get a calculator. 15 to the power of 2. Oh yeah, 225. So negative 225 divided by 250, or divided by 500. That's not the best. Here we go, by 500, since 2 times 250 is 500, is equal to our alpha, our angular acceleration, which puts our angular acceleration at negative 0.45. Make sure to put units, radians per second squared. Now using this, we can find time if we simply plug into our first equation, which states that final angular velocity is equal to initial angular velocity plus alpha times time. So we plug in numbers, well, 0 equals 15 plus negative 0.45 for our alpha times time. So let's isolate our variable time. Negative 15 over negative 0.45 equals time, and this tells us that our time is equal to 33.3 repeating seconds. And yeah, that's it. Hope this helps. Bye.